Welcome to Tomorrow Unveiled. We are opening the hangar doors on the future of physical work because robotics is not merely having a technological moment, it is hitting a massive, irreversible inflection point.
It really is.
Yep.
For years, we've all seen the flashy university lab demos, the prototypes. It's been very coming soon.
Exactly, always just around the corner. But the consensus that's emerging from all the sources our dedicated research team has compiled, it suggests that 2025 is the year. It's the definitive year that robots are leaving the research bench.
And heading straight for scaled deployment.
Mm-hmm.
We're talking about the factory floor, the deep warehouse, and even, these incredibly delicate medical applications.
And those applications require millisecond safety responses and just an extraordinary level of AI dexterity. It's a whole new ballgame.
That's the critical takeaway. The information we reviewed highlights this powerful combination of drivers. It's not just one single breakthrough.
Right.
It's the maturity of mass manufacturing capabilities, finally meeting a fierce commitment to these rigorous millisecond-level safety requirements.
And that's all combined with these genuine functional leaps in AI architecture, right? Specifically, deep reinforcement learning.
Exactly. So our mission today on Tomorrow Unveiled is to really strip away the hype. We want to focus specifically on the corroborated facts, the technical, the logistical achievements that are actually enabling these machines to transition into these complex, unpredictable, real-world environments.
And what a transition it is. We're going to start with that foundational shift. The first confirmed mass delivery of industrial humanoids. The moment the supply chain actually meets real industrial demand. Then we're going to take a really detailed look at the extreme engineering required for human safety. We'll analyze how researchers are using these advanced AI architectures to achieve reaction speeds faster than any human, which that's a complete game changer for collaboration.
It is. And following that, we'll dive into what's being called the physical AI bottleneck. We'll explore how new control methods, like attention-based AI, are finally tackling that monumental challenge of robot dexterity. We've got a fascinating example for that, a robotic throwing task.
A throwing task, okay. I'm intrigued.
And finally, we'll expand our view to the entire machine ecosystem. We'll look at non-humanoid industrial intelligence, like agentic AI for inspection, and then we'll get into the dizzying rapid progress happening in healthcare.
Everything from brain-computer interfaces to AI-powered cancer cell reprogramming.
It's a packed agenda.
Let's get into it. Let's start with the big picture, because the underlying reality here, the real story, is scale. For so long, the conversation has just been, when will robots be ready?
Right. When's it going to happen?
And the sources we have suggest the answer is they are ready now and they are shipping. Industrial humanoids are actually moving from R&D into genuine, large-scale production.
This is so significant. The research team documents what's being claimed as the world's first mass delivery of industrial humanoids. And you said it before, this isn't just a handful of prototypes for testing anymore.
No.
This is the start of a serious commercial rollout, and that requires a robust manufacturing infrastructure that, frankly, has been lacking in the sector until very, very recently.
So give us the specifics on that milestone. Who is driving this and just how big is this deployment, really?
Okay, so the company is UB Robotics. They're based in Shenzhen.
Right.
And they've successfully transitioned into mass production. They've already shipped hundreds of units of their Walker S2 industrial humanoid robot.
Hundreds, wow. And who's buying them?
They're delivering these units to major manufacturing and logistics partners. We're talking heavyweights in the automotive sector like BYD, Geely Auto, FAW, Volkswagen.
So the big players.
The biggest players. And alongside them, global electronics manufacturers like Foxconn. When you see industrial behemoths like that taking on hundreds of units, you just know the technology has finally reached a tipping point of reliability.
And crucially, that reliability is being backed up by genuine capital investment. This isn't just vaporware funded by a round of venture capital. These are hard, concrete industrial purchasing decisions.
Exactly. The order books really substantiate this shift. UB Tech, they've secured orders exceeding 800 million yuan.
Which is, what, in dollars?
That's approximately 113 million US dollars for delivery in 2025. And they have a target delivery of around 500 of these Walker units slated for completion by the end of this year.
500 units in less than 12 months?
That kind of volume. It's just unprecedented in the industrial humanoid space. It really marks the shift from a technology demonstrator to, a real capital asset purchase.
But the core industrial environment, it demands relentless productivity. If a robot is replacing a human shift worker, it has to be able to work 24/7. So given limitations we all know exist with battery density, How is UBTech addressing that endurance problem? Because we all know downtime is absolute poison in a factory setting.
That's the critical logistical puzzle they seem to have solved.
Hmm.
I mean, achieving 247 continuous operation in a factory it's just impossible if the robot needs a human to come over and manually manage charging cycles every few hours.
It breaks the whole model.
It does.
Uh-huh.
Their solution is an autonomous battery swapping capability. The Walker S2 can detect its own low power, navigate itself to a swapping station, replace its own power source, and then get back to work.
Okay, how long does that take?
About 3 minutes. And all without any human intervention.
3 minutes? That's faster than an average pit stop in Formula One. When you compare a 3-minute outage to, say, a 30-minute charging break, it completely changes the entire cost equation for the factory owner.
It really does.
This one single feature, this autonomous swapping, it feels like the real gateway to industrial viability.
It absolutely is. It turns the robot from just another piece of automated equipment into a continuous industrial asset. But beyond the physical hardware, there's also this major shift in the underlying business model that the research team highlighted.
Let me guess, they're not just selling standalone hardware anymore.
You got it. They're not just selling a robot in a box.
They're selling a comprehensive ecosystem, a turnkey solution.
Precisely. They are selling integrated systems. And this includes a full software stack, like UBTech's co-agent AI system, and these really sophisticated fleet coordination platforms.
So the goal is to make it seamless.
Exactly. The goal is to ensure seamless integration with the existing factory execution systems and warehouse networks that are already in place. The robots have to be able to ingest complex task instructions, plan multi-step actions across different environments,
And coordinate their movements with other robots and with the human workers.
right, all through a single software platform. And this move from standalone hardware to these deeply integrated turnkey systems, that's perhaps the most important logistical requirement for achieving true industrial scale.
So if the Walker S2 represents the start of this mass production, we should also look at other deployments across other high-value sectors just to confirm that this industrial confidence is widespread.
Definitely, and the transition is sector-wide. We saw data confirming that Agility Robotics' Digit Humanoid, for instance, demonstrated remarkable operational reliability.
The Digit, right, I've seen videos of that one.
In a continuous operation demonstration, it was focused on bulk handling tasks, and Digit achieved a 98.96% success rate over a 28-hour period.
99% over more than a full day.
That level of near-perfect execution signals to logistics partners that the fundamental perception and movement models are finally sound enough for real-world application.
And we're seeing that same confidence in major manufacturing too, right? Aptronics Apollo, for example, is already being piloted at Mercedes-Benz manufacturing facilities.
Correct. Focusing on tasks that are valuable, but, very repetitive. Things like parts delivery and component inspection.
But I think the most compelling example of this rising confidence in AI-driven physical robotics that involves these safety-critical environments, the research team highlighted a very specific deployment.
Yes, a humanoid robot named Hoxo. It's built on a standard hardware platform, but it's been integrated with this proprietary physical AI software. And it's being tested at a French nuclear facility.
A nuclear facility, you can't get much more high stakes or hazardous than that. What is Hoxo's mission there?
Its mission is autonomous inspection and the execution of technical gestures inside the facility. I mean, this just shows an extraordinary level of trust in the physical AI's ability to operate autonomously in places where human error is just completely unacceptable and radiation exposure has to be minimized.
So the industry is clearly seeing humanoids not just as a labor substitute, but as a critical safety enhancement tool.
Absolutely, for tasks that are either too dangerous or, frankly, just too monotonous for humans.
That transition we just discussed, moving from robots that are caged off, doing repetitive work, to robots collaborating right alongside humans in a factory or even a nuclear site, it means that safety is no longer just a checkbox.
Oh, not at all. It becomes this extreme engineering challenge, and it's governed by physics and by timing.
Right. When a human moves unexpectedly or drops something, the robot can't just freeze up.
It has to instantaneously sense that disruption, decide on a new collision-free path, and begin executing that new path. And that reaction time, the whole sequence, is regulated by unbelievably strict temporal constraints.
And the research team really honed in on an industrial standard that defines the absolute boundary for this kind of safety. What is that critical timeline we're talking about?
The constraint is 25 milliseconds. 25.
A 40th of a second.
Exactly. Industrial standards stipulate that the trajectory replanning delay, that's the time it takes for the robot to react to a sudden dynamic disturbance, must be controlled within that 25 millisecond window.
And for context, what do traditional algorithms manage?
Well, to give you that context, traditional trajectory planning algorithms, even when they're highly optimized, often average delays of over 45 milliseconds.
So almost double the safety limit.
Right. And if you're moving a heavy payload, that 20 millisecond gap is the difference between an uncomfortable pause and a serious, potentially life-threatening collision.
Okay, so if 45 milliseconds is typical and 25 is the absolute safety threshold, how is mass deployment even possible?
This is where the major breakthrough comes in. The data compiled by our research team documented a new deep reinforcement learning framework that successfully compressed this critical delay down to an average of 18.3 milliseconds.
18.3.
In a complex 7-degree of freedom system.
Yeah.
So this isn't just meeting the threshold, it's completely shattering the industrial safety standard.
18.3 milliseconds. That is just astonishingly fast. And what was the reported impact of this breakthrough?
The documented result is a reduction in the accident rate in human-robot collaboration by 2 orders of magnitude.
2 orders of magnitude. 100 times safer.
Think about what that means in a massive industrial operation. It means the perceived liability, the associated insurance costs, they just plummet. And crucially, worker trust in the technology skyrockets. This speed breakthrough is the technical gatekeeper for wide-scale collaborative deployment.
Okay, so let's unpack the engineering. How does the AI actually achieve this rapid, low-latency performance? If the old method was too slow, what is the core architectural innovation that's delivering that 18.3 millisecond speed?
It's a technique they call dynamic hybrid replanning.
Dynamic hybrid replanning, okay.
So traditional, slower methods, they try to recalculate the robot's entire path, this really costly global path calculation, every time an obstacle appears.
Right, they start from scratch.
Exactly. The dynamic hybrid replanning system avoids that expensive process. Instead, when a sudden disturbance is detected, the AI uses a highly efficient local optimization approach. It just executes the safest, most immediate local movement necessary to avoid the obstacle. And then, using what's called a greedy path reconnection strategy, it efficiently tries to latch back onto the original, pre-calculated global path. That combination of immediate local safety response and efficient global path re-engagement is what delivers the speed.
So it's essentially the robot deciding, don't panic and rethink the whole journey, just step around the immediate problem and get back on track.
That's a perfect analogy for it.
Speed is one thing, but as we touched on earlier, human-robot interaction has to feel smooth. A fast but jerky, unpredictable robot is still terrifying and dangerous.
Oh, absolutely.
So how do they ensure the movement isn't just fast, but exhibits what the researchers called biomechanical naturalness?
This involves leveraging a highly specialized mathematical concept, the use of hyperbolic-space representation.
Okay, you're going to have to give us an analogy for that one, because that sounds pretty esoteric.
It does, but we can break it down.
Yeah.
Think of traditional robot programming as navigating on a flat map. That's Euclidean space. Every decision, every turn, is discrete and often leads to these stiff, angular movements.
Like a machine programmed with only straight lines and hard turns.
Exactly. Hyperbolic space, however, has a constant negative curvature. So, imagine you're walking on the surface of a saddle, or maybe the inside of a bowl that curves away from you in all directions.
Okay, I can picture that.
By mathematically defining the robot's joint movements within this curved hyperbolic geometry, the system essentially forces the joint movements to follow these natural, continuous, gentle arcs.
So the math itself encourages smoothness.
Right. This representation mathematically bridges the continuity of biological joint motion, the natural smoothness we see in ourselves, with the necessary discreteness of the digital algorithms. The result is a system that successfully suppresses what they call acceleration mutations, or joint jerk.
Joint jerk, I like that term.
It keeps the movements within defined safety and comfort limits.
That is a fascinating application of advanced geometry to physical robotics. It's really about making the robot move like an organic system, even though it's all digital at its core.
And that naturalness is absolutely critical for human acceptance and trust. But beyond that, we have to consider the robot's behavior in these unpredictable, unstructured environments. If the factory floor is constantly changing, tools moving, personnel shifting, a single program strategy is going to fail, and fail quickly.
So they need adaptability, or what the research team was calling strategy diversity.
Yes, exactly. To prevent the robot from collapsing into a single, vulnerable behavior when it faces these random dynamic disturbances, the system is engineered to maximize what's called strategy entropy.
Entropy. So introducing a kind of useful randomness.
In a way, think of entropy in this context as a measure of unpredictability or, again, diversity in the robot's policy choices. If a robot only has one way to safely avoid a collision, and that one path gets blocked, it fails.
To the dead end.
Right. But by maximizing strategy entropy, the AI ensures it has this wide and robust portfolio of different safe actions it can immediately deploy. The researchers found this mechanism increased the diversity of successful strategies by over 85%.
85%? That's huge.
It is. It ensures the robot can navigate these multi-obstacle scenarios with a consistently high success rate, which is a non-negotiable feature for real-world deployment.
And as this technology moves into the real world, I imagine the regulatory side has to catch up. The research also touched on new standards that are codifying these safety requirements.
Indeed. The revised ANSI 3 R15.06 2025 standard is a significant evolution. It shifts the regulatory focus from just regulating the robot hardware itself to regulating the collaborative application as a whole system.
So it's not just about the robot, it's about how the robot is used.
Precisely. And this introduces essential new concepts like speed and separation monitoring, or SSM. That's where sensors dynamically dictate how fast a robot can move based on how close it is to a human.
And the other one was power and force limiting.
TFL, right? That physically constrains the robot's maximum output force so that any accidental contact remains completely non-hazardous.
Finally, on this topic, we have to address stability. Real industrial environments are, well, they're messy. Sensor data is noisy, lights flicker, things get dusty. If the AI is built on perfect lab data, it's going to fail instantly when it gets exposed to all that inevitable input noise.
That's the reality check, isn't it? The research team highlighted the superior robustness demonstrated by some advanced deep Q network variants, specifically double deep Q networks with noisy weights, or DDQNN.
DDQNN, okay, that's a mouthful. Let's break down why adding noisy weights helps with noisy input. It sounds a bit counterintuitive.
It really does. But the noisy weights component refers to adding stochastic noise, basically controlled randomness, to the network's own parameters during training. This forces the agent to explore more and help to find more robust policies.
So you make it a little unpredictable on the inside so it can handle unpredictability on the outside?
That's a great way to put it. When the system was exposed to real-world input sensor noise, like zero-mean Gaussian noise applied to the joint positions, the DDQN approach maintains stability and superior performance compared to standard DQNs. By training the network to be slightly random internally, it became less susceptible to external randomness.
Ensuring resilience and stability in those dirty, real-world manufacturing environments.
Or a standard, overly deterministic DQN might just become unreliable very quickly.
So we've established the scale of deployment and the critical safety engineering required. Now we have to move to the core utility of the humanoid form itself, dexterity. If a robot can't handle a complex tool or pick up and manipulate these fragile, oddly shaped objects, its potential is just severely limited. Dexterous manipulation really does remain the last great hurdle.
It is the final frontier, as you say. It forces researchers to abandon those simple pick-and-place routines and develop entirely new AI control methods for very complex motor skills.
And the research team provided a fascinating window into this challenge by looking at a very specific test case they use in deep learning, the robotic throwing task.
It's a great example.
Throwing. Why would a factory robot need to throw things? It seems a bit odd.
It's not about tossing inventory across the warehouse, although who knows, maybe one day. It's a critical test because throwing an object requires a continuous, high-precision, dynamic maneuver.
Ah, I see.
The robot manipulator has to adjust all his joint parameters in real time. It's calculating velocity, release angle, trajectory, all while aiming for an unknown target under high uncertainty. It's a perfect simulation for high-speed, dynamic adaptation.
So things like catching or rapidly placing delicate objects or interacting with a moving conveyor belt.
All of the above. And in comparing various DQ learning or DQN algorithms for this specific task, the results pointed very clearly toward a single winner, attention mechanisms.
Right. The findings were decisive from what I read. DQN with multi-head attention, DQN-MHA, significantly outperformed all the others.
It wasn't even close. It delivered a higher total average return, which is a key metric for overall learning success, and, maybe more importantly for real-world application, it demonstrated vastly superior generalization ability.
What does that mean in this context?
It means it could successfully throw to a new target location without needing a complete retraining cycle. It learned the skill, not just the one task.
So let's break down that attention mechanism for everyone listening. We hear about attention all the time in the context of large language models. How does multi-head attention allow a physical robot to focus and perform so much better than the older DQN models?
Okay, think of it like this. A standard DQN model looks at the entire input state, all the joint positions, velocities, target coordinates, as a single, undifferentiated stream of data.
It's all just one big pile of numbers.
Pretty much. Multi-head attention, however, enables what is called horizontal self-attention. The AI uses multiple parallel heads, and each one is equipped with different learned weights. These heads all process the same input state simultaneously, but each head is trained to focus on a different critical relationship within that data.
So one head might be exclusively watching the object's current velocity, while another one is focusing on the difference between the robot's gripper orientation and the target location.
Precisely. It allows a model to prioritize different critical features all at the same time. It filters out the noise and focuses only on the high-value variables that are essential for trajectory prediction and dynamic timing. It's like having several expert decision-makers reviewing the same data at once, which leads to a much more efficient and context-aware decision.
Now, the research also mentioned a structured self-attention approach, DQNSA, which uses vertical or sequential attention layers. Why did the parallel approach of DQN-MHA win out over that hierarchical, stacked approach?
That's a subtle but really important distinction. The DQNSA approach, it generates a hierarchical abstraction. Each attention layer processes the input and then passes its refined output to the next layer up. So it's building this deep sequential abstraction of the problem.
Which sounds powerful.
And it can be, for something like complex linguistic analysis. But the researchers found that for the specific real-time dynamic needs of the throwing task, the DQN-MHA's ability to generate diversified parallel focuses just proved more effective. The time-critical nature of throwing benefits more from simultaneous expert analysis than it does from a deep sequential one.
This progress in dexterity is exciting, but it brings us to the massive underlying industry challenge that all these innovations really depend on: the physical AI bottleneck.
Ah, yes, the bottleneck. It is singular and it is critical. The severe lack of sufficient high-quality training data generated in the physical world.
Right. Deep reinforcement learning models, they need millions of real-world interactions to achieve robust, general-purpose autonomous behavior.
And unlike LLMs, where text data is just abundant, every single data point for a robot requires a real physical interaction in time and space. And that is slow, and it is very expensive to generate.
So the industry is now building tools specifically to solve that problem. The research team detailed 2 major hardware and software solutions introduced just this week that are aimed explicitly at solving this data deficit.
That's right. First, we saw Unitary Robotics introduce the G1D. This is a wheeled humanoid platform, but it's explicitly marketed and positioned as a data acquisition tool.
A data-gathering robot.
Exactly. It features high-definition stereo cameras on its head and another camera right on its hand. The platform's primary purpose is just to generate high-quality perception data, the kind that's necessary for training these complex manipulation models. They're effectively selling a specialized tool for generating the required training data, not just a final product.
That's a real shift in focus. It's like selling the shovel during a gold rush, not just the gold.
That's a perfect way to put it. And the second solution focuses on leveraging human expertise through high-fidelity teleoperation data. Training often relies on foundational data generated by human operators controlling the robots.
So to make that scalable and precise?
You need better tools. Movella's Exens brand launched the next-generation Exens Link motion capture system.
And how does that help robots?
The system uses low-latency Wi-Fi 6E to stream extremely high-fidelity human motion data. We're talking subtle joint rotations, wrist movements, all of it, directly to the robotic models. This facilitates the crucial human-in-the-loop data generation. It reduces the latency to about 20 meters for real-time teleoperation.
Which is vital for transferring those subtle human movements and learned manipulation techniques into robot policies with the precision you need.
Absolutely.
And finally, our sources confirm that this focus on data is leading to breakthroughs in highly specialized manipulation capabilities that go way beyond simple grasping.
Yes. specifically in the area of fine internal object manipulation. A new neural dynamics model, called DexNDM, was introduced that enables robots to perform high-precision in-hand rotations of objects.
So, like a human using their fingers to adjust a pen's position without dropping it.
Exactly that. This model allows the robot to reorient objects with all sorts of different geometries, from tiny microelectronics to complex structural parts, regardless of the hand's current orientation. This opens the door for complex assembly tasks or precise insertion maneuvers in really hard-to-reach places.
And that progress is being backed up by the numbers.
Absolutely. Other research confirmed this trend, showcasing a high-dimensional dexterous hand control system that achieves success rates of 94.6% across 512 different real-world objects.
512 objects. Wow.
A 94.6% success rate across that many diverse objects. It just confirms that the underlying AI is learning the fundamental physics of fine motor skills, not just a bunch of rote movements.
We've seen the incredible engineering that is enabling the rise of the machines, from millisecond safety to dynamic dexterity.
And before we pivot to the broader machine ecosystem, and we're going to look beyond humanoids at everything from industrial inspection to some really amazing medical breakthroughs, let's just take a quick moment to pause.
If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveil, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
While all the humanoid news has generated the largest headlines, the core AI breakthroughs we've discussed, low latency, dynamic path planning, those advanced attention mechanisms, they're rapidly benefiting all robot types. It's dramatically expanding the entire machine ecosystem.
And a great example of agentic AI moving into critical industrial inspection involves a very familiar non-humanoid form.
That would be Boston Dynamics' quadruped robot, Spot.
Of course.
Spot is being combined with industrial AI software platforms like IFS.ai. This creates these fully autonomous inspection and maintenance systems that are tailored for asset-intensive industries like energy and heavy manufacturing.
So it's an end-to-end agentic system.
It is. Spot acts as the mobile, multi-sensory data collector, and then the AI platform acts as the decision engine. It identifies anomalies and recommends action.
The sources gave a really tangible example of the value this is delivering at a food manufacturing plant. What specifically did they find?
At a facility like Cargill's Amsterdam plant, the deployment of Spot is demonstrating its utility as a very sophisticated early warning system.
An early warning system? How so?
Spot performs approximately 10,000 autonomous inspections every week. It's capturing thermal, acoustic, and visual data across this huge facility. And critically, the robot has already detected equipment, like a decanter, that was running above its safe operating limits.
Things a human might miss.
Exactly. It also identified fluctuating bearing temperatures that humans just wouldn't notice. This allowed for preventative maintenance before a catastrophic failure could occur.
And the strategic goal here, as emphasized by the research team, is explicitly to augment human expertise, right?
Yes, very explicitly. The goal is to give the existing operators this data-driven visibility, not to replace the skilled workers.
That makes perfect sense. These machines are becoming these smart, mobile sensor platforms. And this global push for smart manufacturing is accelerating R&D through some major partnerships.
Yeah, absolutely. The speed of iteration is being driven by this tight integration between corporations and academia. Hyundai Motor Group, for example, just launched a corporate lab in Singapore.
In partnership with whom?
In partnership with Nanyang Technological University and ASTAR. And the strategic brilliance here is that this lab is located directly inside Hyundai's own smart factory testbed, the HMGICS.
Why does that physical location matter so much?
Because by embedding academic research directly into an operational factory, they are dramatically accelerating the prototyping, validation, and deployment cycle.
Ah, so there's no gap between the lab and the real world.
None. The focus areas are exactly what we've been covering: AI, robotics, 3D printing for advanced manufacturing. Instead of waiting years for a lab result to transfer to a factory, they are testing next-generation technologies on actual production lines immediately.
All right, let's shift gears completely now. Let's move into how AI is affecting the biological and medical domains. We can start with the latest progress in brain-computer interfaces.
Okay. Elon Musk's Neuralink successfully implanted its device in a second patient this year, which gives us a crucial point of comparison for the technology's rapid progress.
Right, the first patient, Nolan Arbaugh, he made a lot of headlines, but from what I recall, he only had about 15% of his channels operational, yet he could still interact with technology.
That's right. Now, for the second patient, the research team noted that the second implantation reportedly went extremely well. They have 400 out of 1,024 electrodes functioning reliably.
400, so that's a massive jump in functional capacity, from 15% to nearly 40%.
It is. It suggests a very steep learning curve in both the surgical technique and the device reliability itself. It's moving the technology closer to truly robust human augmentation.
Next up, in oncology, the research detailed an AI-powered technique for fighting glioblastoma.
Which is, tragically, one of the deadliest brain cancers. And this is a truly revolutionary application of AI-guided genetics. Researchers at USC discovered an AI-powered way to fight it by genetically reprogramming the cancer cells themselves.
Reprogramming the cancer cells? How?
They managed to essentially hijack the cancer cells and turn them into dendritic cells.
And those are the critical cells that activate the immune system?
You got it. So the cancer cells basically become these tiny immune boosters.
That's incredible. What were the results like?
In mouse models, they were extremely promising. This innovative approach, when it was combined with standard immune checkpoint therapy, boosted survival rates by up to 75%. This could represent a potential paradigm shift in cancer treatment.
Not just for glioblastoma,
But by offering a blueprint for using the body's own defense mechanisms against other challenging cancers.
And finally, on the medical front, we saw new data comparing diagnostic AI directly against human physician judgment, which is always a contentious area.
It is. The study compared GPT-4V, a large vision model, against human physicians on 207 image-based diagnostic challenges.
And the results?
The AI achieved 81.6% accuracy, which was slightly higher than the physician's 77.8% accuracy. So on the surface, this just confirms the growing capability of AI in quick clinical diagnosis.
However, there's always a however. The critical takeaway here, and the reason human judgment remains paramount, it isn't the accuracy score itself, it's the flaw in the AI's reasoning.
That's the crucial caveat. While the AI matched or even exceeded diagnostic accuracy, it struggled significantly with explanation. Its rationale was often flawed, with error rates in its reasoning reaching up to 27%.
So the AI could arrive at the correct destination but travel via the wrong road.
That's a perfect way to describe it. This inability to reliably articulate why a diagnosis was made, it just underscores the absolute necessity of human oversight and critical thinking in clinical settings.
Because explaining the rationale to a patient or another doctor is just as important as the diagnosis itself.
It is.
And lastly, on the automation side, specialized robotics is moving into some highly precise procedures.
Yes. The development of an autonomous robot dentist was noted. It performed the world's first human dental procedure.
A robot dentist, what did it do?
It successfully prepared a tooth for a crown in about 15 minutes. This is a clear demonstration that specialized automation can achieve really rapid speed gains and ultra-high precision in specific repetitive medical tasks where the environment is highly controlled. We have covered some massive ground here on Tomorrow Unveiled, and it really confirms that the shift is real. From mass delivery schedules of humanoids and millisecond-level safety engineering
to the breakthroughs in attention-based dexterity and these revolutionary medical applications.
We are clearly in a pivotal phase where hardware readiness and these profound AI breakthroughs are finally meeting real-world industrial and service trials.
And the economic projections, they just reflect this foundational shift. The market analysts the research team cited are projecting staggering growth. The global humanoid robot market is estimated to swell to $51 billion by 2035.
$51 billion.
With forecasts suggesting that tens of millions of humanoids could enter the workforce by 2050. I mean, the machine revolution is not some distant promise anymore. It's accelerating exponentially, and it's quantified by billions of dollars in actual orders.
However, to maintain a balanced perspective, the sources compiled by the research team did include two vital cautionary notes. And these really temper the current enthusiasm and remind us of the gap between lab conditions and the real world.
The first one reminds us just how sensitive this hardware still is to environmental variables. It references the very public demonstration of Russia's humanoid robot, Adol.
Correct. Adol. It face-planted during its public debut. And it was due to technical sensitivity, specifically related to lighting and calibration issues affecting its stereo cameras.
A simple lighting change.
And it highlights that these systems are still highly brittle outside of controlled lab settings. ensuring reliable, generalized autonomy in the variable, unpredictable real world remains a persistent and very expensive engineering challenge.
And the second, more concerning note relates directly to the generative AI models that are intended to be the brain for many of these systems.
Yes. In high-fidelity simulations, general AI models that were tested for robot control have been shown to approve commands that could cause harm. Their failure modes weren't just physical errors. They failed basic safety and ethical discrimination tests.
Which is terrifying.
It is. And it's prompting experts to urge for strict independent safety certification, comparable to the rigorous standards used in aviation or medical device manufacturing. When we consider the widespread deployment we were just talking about, these safety layers have to be built from the ground up, not just patched on later.
We would love to hear your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this accelerating transition of robots and machines into our everyday lives, especially that 18.3 millisecond safety barrier.
And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly does help us reach new listeners interested in these pivotal technological moments.
So we'll leave you with this final provocative thought. The engineering advancements we discussed today mean that robots are learning to move with human-like fidelity while responding faster than any human possibly can. But if an AI system can match human diagnostic accuracy in medicine, yet it struggles to explain why, with a 27% error rate in its own rationale, what ethical or liability trade-off must society accept when we deploy these powerful yet opaque systems in safety-critical fields like medicine and human-robot collaboration?
If performance and speed come at the cost of explainability, what value do we ultimately place on transparency? How much performance are we willing to trade for that human assurance?
Thank you for joining us on Tomorrow Unveiled.